Hello, this is Mrs. Decker, and this is Objective 2A on specific heat capacity. So first we're going to define what specific heat capacity is, and then we will use it in a formula to calculate the heat transfer from one substance to another. Specific heat capacity is the amount of heat in joules required to raise 1 gram of a substance by 1 degree Celsius. The symbol we will use for specific heat capacity is a lowercase c, and the units are joules per gram degrees Celsius. So an example of a specific heat capacity is for water, it is 4.184 joules per gram degrees Celsius. And that 4.184 should look familiar to you. If you remember back in Objective 1C when we were doing our energy conversions, 4.184 is the amount of joules in 1 calorie. Each compound or element will have its own unique specific heat capacity due to its composition, what it's made of. So here are just a couple of common ones for copper, granite, lead, ice, and water. Now, you are not required to memorize any of these. If you need them, they will be given to you. Sometimes you will be solving for the specific heat capacity, though, so in that case, it won't be given to you. So here is our specific heat capacity equation. It is Q equals mc delta T. So the lowercase q represents the heat energy transferred in joules. Lowercase m is the mass of the substance in grams. Our lowercase c is our specific heat capacity in joules per gram degrees Celsius. And delta T is the change in temperature in degrees Celsius. It must be in degrees Celsius. Now remember the little triangle here means delta, and delta is a change. So here, anytime you see delta T, we're looking for a change in temperature, and it's always going to be the final temperature minus the initial temperature. It's very important that you not mix those up, and we'll talk about why in just a second. So remember, we're focusing on heat transfer in this unit. And in endothermic reactions, heat is absorbed by the system. So our Q is going to be positive. And remember, Q is the heat that is transferred. So it's transferring into the system, it will be positive. And now for exothermic reactions, remember heat is released from the system to its surroundings. So Q is going to be negative. And this is why it's important for you to read and make sure you are labeling the final and the initial temperatures correctly, because our delta T might be positive or negative based on whether it's an endothermic or exothermic reaction, which will affect the sign of Q, which is important. So here is our first example. If the temperature of 7 grams of water increases from 15 degrees Celsius to 65.5 degrees Celsius, how much heat was absorbed by the water? Now remember, our equation is Q equals mc delta T. So we want to start by labeling all of our given information. So we are given 7 grams, which is our mass, and it's increasing from 15 degrees Celsius to 65.5 degrees Celsius. Our initial temperature is 15 degrees Celsius, and our final temperature is 65.5 degrees Celsius. Now the question is asking us for how much heat was absorbed by the water, which is Q. We have M, we have our initial temperature and our final temperature. All we need is C. C, remember, is the heat capacity of water, which is 4.184 joules per gram degrees Celsius. So now we have every variable except for Q, so we're going to plug that all in. And remember, final temperature minus initial. So when you solve for Q, you get 1,480 joules. And remember, we want to stay with 3 sig figs, so make sure you're rounding your answer to 3 sig figs. Okay, and example number 2 says a sample of water gives off 982 joules of energy when the temperature drops from 50 degrees Celsius to 24 degrees Celsius. What is the mass of the water sample? So now our Q is given to us. It says that 982 joules of energy is given off. So that means that heat is released from the system to the surroundings, so that needs to be a negative 982 joules. And the temperature is dropping from 50 degrees Celsius to 24. So our initial temperature is 50 degrees Celsius, and our final temperature is 24 degrees Celsius. And we're looking for mass. So, and we're talking about water. So our specific heat capacity, again, is 4.184. So now we're going to plug everything into our equation. Okay, and we're going to be solving for mass. So you need to remember your algebra. And you should get 9.03 grams for the mass. Now, example number 3 says a 43.9 gram sample of iron has a specific heat capacity of 0.45 joules per gram degrees Celsius. What was the final temperature of this sample if the heat absorbed was 82.3 joules and the initial temperature was 47.3 degrees Celsius? So let's write our given information. All right, so our mass is 43.9 grams. The heat capacity of iron is 0.45. Our initial temperature is 47.3 degrees Celsius. Our final temperature is what we're looking for. So our Q is 82.3 joules. So we want to plug everything into our equation. Minus 47.3. So now to solve this, you are going to multiply 43.9 times 0.45. Then you'll take that and divide 82.3 divided by your answer here, and then add 47.3. So you need to remember your algebraic order of operations. So when you solve this, the final temperature you should get is 51.5 degrees Celsius. Okay, and our last example says how much energy would be needed to heat 450 grams of copper metal from a temperature of 25 degrees Celsius to a temperature of 75 degrees Celsius. So our mass is 450 grams. Our heat capacity is 0.385. Our initial temperature is 25 degrees Celsius, and our final temperature is 75 degrees Celsius. So we're going to plug everything in and solve for Q. So when you solve for Q, you get 8,660 joules. Remember, round to 3 sig figs. So now the next page of your packet has some practice for you to work on. So go ahead and work on that practice and let me know if you need help.